Hey everyone, and welcome. Today, we're going to pull back the curtain on the hidden language of our digital world. You know, the stuff that turns a simple satellite photo into a super powerful map. So let's get right into it. What is raster data?
Okay, so picture a satellite image of Earth in your mind. At first glance, it's just a photo, right? But what if every single tiny dot in that picture held a secret? A piece of information just waiting for us to find it. That's exactly what we're going to dig into today.
You see, to really get what's going on with the maps we use every day, you've got to look beyond the pretty picture. We need to zoom in, like way in. We need to see the actual data that makes the whole thing tick. So at its core, raster data is actually pretty simple. Just imagine we could lay this giant sheet of digital graph paper over the entire Earth. Every single little square on that paper is a cell, or what we call a pixel. And here's the key. Inside each one of those pixels is a number, just a single number that tells us something about that exact spot on the ground. And believe me, this isn't just some abstract idea. This is literally how modern tech sees our world. Think about it. Satellites like Landsat 8 or Sentinel 2, aerial photography from drones, even old-school scan maps, they all create this type of data. It's like they're turning our entire planet into one massive organized spreadsheet. Okay, let's talk a little more about that grid structure. You know how when you zoom way into a digital photo on your phone, eventually you stop seeing a smooth picture and you start seeing the little squares, right? Those are the pixels. It's the same exact idea here. Those are the building blocks of the map. And this is the most important part. Every single one of those pixels doesn't just hold a color. No, it holds a number, a numeric value. That number, well, that's its story. It's the key piece of information for that specific little square of the Earth. So, okay, a pixel holds a number. Big deal, right? Well, yeah, it's a huge deal, and here's why. That one little number is incredibly powerful because it can represent all sorts of different things, depending on what we're trying to measure. Basically, the values in these pixels come in two main flavors. First up, we have what's called continuous data. Just think of anything that changes gradually, flows from one value to the next, like temperature or the height of a mountain. It's like a smooth ramp. And then you've got discrete data. This is for stuff that fits into neat, separate boxes or categories, things like land use. Think of these as separate building blocks. Let's take a look at discrete data in action, because it's pretty cool. It's basically like a giant color by numbers for the whole planet. Check out this table. You can see that each number is just a label for a category. So if a pixel has the value 2, the computer knows, hey, that's a forest. If it's a 3, that's a city. It's a really simple but super powerful way to classify the entire world. Now for continuous data, this is the perfect example. What you're seeing here is a digital elevation model, or a DEM. In this case, a pixel's value isn't just a label, it's an actual measurement. So a value of, say, 350 literally means that exact spot on the ground is 350 meters above sea level. You can really see how this would create that smooth ramp of values we were just talking about, right? All right, so we've got our grid of numbers. Awesome. But that's not quite a map yet, is it? We're missing a few key ingredients to turn this raw data into something that's actually useful for, understanding our world. So let's start with a really important question. Does the size of these little pixel squares actually matter? And the answer is, oh yeah, absolutely. This whole idea is called spatial resolution. It's simply the size of the real-world area that one single pixel covers. So a 30-meter resolution, which is pretty common for a satellite like Landsat 8, means each pixel represents a 30 by 30 meter square on the ground. But if you have 1-meter resolution, whoa, now you're talking about a ton more detail. And that's why it matters so much. A scientist tracking huge patterns like deforestation might be fine with 30-meter data. But say an insurance adjuster checking out roof damage on one house, they're going to need that super high-resolution data from a drone. So here's the bottom line. Smaller pixels mean you get way more detail. But, and it's a big but, the file sizes get absolutely massive and fast. It's a constant tug of war between getting all that juicy detail and having enough space to store it all. But what about color? How does that work? Well, a satellite doesn't just snap one picture. It actually captures several different grids for the exact same area, and we call these bands. So one band might only see red light, another only sees green, and a third only sees blue. Then you just stack those grids on top of each other and bam, you get the full color image we all know.
And the really cool part? It's not just for pretty pictures. Scientists can look at bands of light we can't even see, like infrared, to measure all kinds of stuff, like how healthy crops are, all the way from space. And finally, we have the last piece of the puzzle, georeferencing. Honestly, this is kind of the magic step. This is what tacks our digital grid onto the physical Earth. It gives every pixel real-world coordinates, latitude and longitude, so the computer knows exactly where on the planet to place the image. Without this, it's just a floating picture. Okay, so that's the theory. Now for the fun part. Let's see how this all comes together in the real world. And what's wild is you almost certainly use raster data every single day and have no idea.
Remember that digital elevation model, the DEM, we talked about? Well, that's the tech that powers the 3D terrain view in your mapping app. Anytime you spin the globe and see the mountains pop out, you're looking at a raster data set where every single pixel's value is just its height.
Or how about this? Every single time you look at a weather map on the news, yep, you guessed it, that's raster data. Each colored pixel you see on that map is a cell, and its number value is simply the temperature in that spot. And it gets even more powerful. In the world of GIS, which stands for Geographic Information Systems, scientists and city planners use this exact same tech to classify land automatically. By looking at the numbers across all those different bands we talked about, they can map out precisely where the forests are, where the cities are, where the water is, which is, as you can imagine, absolutely crucial for tracking huge issues like deforestation or how our cities are growing. Now, as powerful as this all is, I have to be honest, raster data isn't the perfect tool for every single job. Like anything, it's got its pros and its cons. On the plus side, the advantages are pretty obvious. The grid is simple, and it's fantastic for looking at things that are continuous, like elevation. But the downsides are real too. We already mentioned that high-resolution images can take up a crazy amount of storage space. And also, if you try to show something with a really sharp, precise boundary, like a property line, it can end up looking all blocky and pixelated. So here's what I want you to take away. The next time you glance at a digital map or satellite photo, remember what you're really looking at. It's not just a picture. It's a rich, searchable database. It's a world that isn't just photographed, but is measured pixel by pixel. And that leaves us with a pretty cool question to think about. Now that we have this incredible power to read the story of our planet, what story are we going to choose to read next?